Dear participants, dear friends, hello everyone, and welcome back to our inspiring online seminar series, which we organize for national and international audiences. It is my pleasure and honor to let you know that our today's speaker is Professor Cora Dvorkin, a well-known cosmologist from Harvard University. She will give a great talk about unveiling the nature of dark matter with cosmological observable. The talk is part of Astronomy and Space Sciences seminar series of TÜBİTAK Research Institute for Fundamental Sciences. At the end of the talk, we will have a session for questions, which one can ask by sending a message through chat button of the Zoom platform or just by raising hand. The areas of interest of Professor Cora Dvorkin are the physics of the early universe, the particle nature of dark matter, the source of accelerated expansion of the universe, neutrinos light release. She uses observables such as the cosmic microwave background, the large-scale structure of the universe, 21 centimeter radiation, and strong gravitational lensing to shed light on these questions. Cora Dvorkin was the co-leader of the inflation analysis group for the proposed cosmic microwave background S4 experiment. Prior to this, she was the leader of the dark matter analysis group. Cora Dvorkin is the Harvard representative at the newly NSF-funded Institute for Artificial Intelligence and Fundamental Interactions Board. Cora Dvorkin has been awarded the 2019 US Department of Energy Early Career Award and has been named the 2018 Scientist of the Year by the Harvard Foundation for salient contribution to physics, cosmology, and STEM, science, technology, engineering, and mathematics education. She has also been awarded the Radcliffe Institute Fellowship, as well as a Schatzer Professorship at the Radcliffe Institute. In 2012, Cora Dvorkin was given the Martin and the Beta Block Award for the best young scientist by the Aspen Center for Physics. Cora Dvorkin, born and raised in Buenos Aires city of Argentina. She received her diploma in physics from the University of Buenos Aires with honors. She earned her PhD in the Department of Physics at the University of Chicago in 2011, where she won the Sydney Blumenthal Fellowship for outstanding performance in research. Cora Dvorkin has conducted postdoctoral research at the School of Natural Sciences at the Institute for Advanced Study in Princeton, and at the Institute for Theory and Computation at the Center for Astrophysics at Harvard University, where she was both a Hubble Fellow and an ITC, the Institute for Theory and Computation Fellow. Today, she is here with us, kindly accepting our invitation to join us for this seminar. With this, I want to thank once again Professor Cora Dvorkin for joining us and look forward to her talk. Cora, you're welcome again, and please begin your talk.
Thank you very much. Let me share my screen. Let me share the screen here. Excellent. Oh. Excellent. Do you see it? Do you hear me?
Yeah, we hear you. It looks great. Great.
Great. So Thank you very much for the invitation. Thank you very much, Alikram, for a very, very nice introduction. And I hope everyone is doing well in these very trying times. So sorry?
Thank you.
As Alikram said, I am an associate professor at the physics department at Harvard. And today I will be talking about how we are trying to unveil the nature of dark matter using information coming from cosmological observables at large and small scales. So there. So here's a roadmap of the talk. I will spend some time setting up that we have a very simple model of the universe that works beautifully, but we still have fundamental questions that remain unanswered. In particular, and what will be the focus of this talk, the nature of dark matter. I will be telling you about how we can use gravitational lensing to probe dark matter at small scales. And for this, I will start with a very promising technique that I have been working on over the past year with my research group at Harvard, a statistical measurement of substructure using gravitational lensing. Here is where I will call indirect detection. And then I will also be presenting some recent machine learning results that we had with my group on directly detecting matter fluctuations at small scales. The take-home message will be that we are gathering large amount of data that can really inform us about the nature of dark matter. The vast majority of the talk will be on how we can extract useful information to make progress on this fundamental question in suitable ways. And I will wrap up at the end with some concluding thoughts. So this line of time over here represents 13.8 billion years of the universe. As we all know, the universe began as a hot and dense plasma of particles in thermal equilibrium. It expanded and cooled, and many physical processes happened along the way. Some of them we know pretty well, and some of them are open questions that are the current topics of research. We know that around 400,000 years after the Big Bang, the universe reached a temperature that was cool enough to have protons and electrons combine into hydrogen atoms. This period is known as recombination, although it should be really called combination, since this is the first time this happened, but that's the name it goes under the literature. Since then, the universe became mainly transparent to CMB photons, and photons mainly free stream toward us until the time when radiation from the first stars and quasars reionized the universe in a period known as reionization, about 500 million years after the Big Bang, and about 6% of these photons rescatter. This is the latest number from the Planck satellite. Today, we observe these photons at microwave frequencies and with a temperature of 2.7 Kelvin, which is 270 degrees Celsius below zero. We have a standard model of cosmology known as lambda CDM, and this model has been extremely successful on cosmological scales among a wide array of different observables, from the CMB, temperature and polarization fluctuations, to the clustering of matter and measurements of the expansion history of the universe. Here, I'm showing you the matter power spectrum. So here you see the CMB temperature power spectrum, polarization, and here I'm showing you the matter power spectrum as a function of wave number. Here, small scales are to the right and large scales are to the left. What you can see is that here in this log-log plot, we cover 4 orders of magnitude on each of these axes, in the y-axis and in the x-axis over here. The black line shows the predictions of our lambda CDM standard model of cosmology. And each of these points is a measurement interpreted within the context of this model as a measurement of the power spectrum. So if you look at the blue and orange points, those points come from measurements of temperature and polarization of the CMB by the Planck satellite in this case. The green points show that as the CMB photons come toward us, they transverse the large scale structure of the universe and they move in and out of these gravitational potentials associated with the large scale structure of the universe. And they have their photon paths deflected. This is called gravitational lensing. that alters the pattern that we see in the CMB. And there is a similar effect shown in yellow that shows the deflection of light paths, in this case, not of the CMB photons, but of the CMB emitted by galaxies. And finally, the red and purple points show us the clustering of galaxies and intergalactic hydrogen as measured by the Sloan Digital Sky Survey, or SDSS. What's interesting about this figure is that it's spanning 14 billion years of history. It's spanning 4 orders of magnitude in length scales and a wide variety of cosmological probes. And we can see how the lambda CDM model fits them all beautifully. So let's now move to the smaller scales. Because of our knowledge of structure formation and the fact that it's hierarchical, we do expect an abundance of structure within dark matter halos. And in particular, in the cold dark matter scenario, for example, we expect a high abundance of substructure compared to other dark matter theories. We see the predicted dark matter density for a Milky Way size halo that I'm showing you here. I don't know if you see my cursor. So we can see that there is structure within the halo and it is clearly not empty, but it is unclear how to tie these observations to dark matter theories. And this is what I will be talking about today. So I will be focusing on the CDM part of our lambda CDM standard model of cosmology. And I will tell you about some of the research that we have been doing with my group at Harvard to provide an understanding to the question, what is the particle nature of dark matter, which constitute approximately 84% of all the matter in the universe, 84%, and we still don't know what it is. So in the past few decades, we have measured the large-scale structure of the universe very accurately with many different probes, CMB, Lyman alpha forest, with gravitational lensing, etc., etc. And this has allowed us to put precision level limits on different kinds of dark matter scenarios. On smaller scales, however, there is a lot of structure, but it is not as well understood. Furthermore, many dark matter scenarios that agree at large scales by construction show differences at small scales. So small scales provide fertile ground for testing these different dark matter scenarios. And we will be using in this talk the smallest scales to either falsify or corroborate the CDM paradigm. So in particular, I will talk about probing dark matter substructure via strong gravitational lensing. And I will start by telling you about a promising technique that we have been working on with my group over the past years based on substructure statistics. So our goal will be to map the distribution of dark matter on small scales in halos of galaxies. And our tool for this will be strong gravitational lensing. So let me give you here a review in one slide of gravitational lensing. We will have a background source at some high redshift and a foreground, and there will be a foreground galaxy that deflects the light because of gravity. So from our perspective, we see extended arcs over here. And the idea will be to use these images to see if the lensing galaxy is clumpy or smooth. This is the lens equation that I'm showing you here in red. And you can map an image back to the source plane by a deflection angle field, which is the gradient of the gravitational potential of the main mass acting as a lens. So this idea that has been suggested about 20 years ago is that substructure in the halos will locally perturb lens images. So by looking at the residual between the image predicted by modeling the lens as a smooth mass and what is actually observed, we can infer the presence of subhalos. The advantage relative to other methods for detecting dark matter is that we do not need to assume a coupling between the standard model and dark matter. So in contrast, for example, to direct detection and indirect detection experiments like and colliders. So in this sense, we are model independent. And another main advantage of the technique I will tell you about is that we will be focusing on the lowest mass subhalos, as you will see. So we can minimize, or we can hope to minimize baryonic feedback. So the lens galaxy will have small scale structure, and this will cause a small deflection as the light from the source crosses the lens. And if you don't have superpowers in your eyes, you will not be able to see any difference between this unperturbed and perturbed image that I'm showing here. So these are actually the image residuals once we subtract the smooth model of the lens. And we are talking here about a % level effect on the surface brightness map of this lens galaxy. You can see from here to here, this is a % level effect, and these variations are caused by having substructure in these lens galaxies. So we can individually detect the higher mass subhalos, and this has been done in many works in the literature. However, the numerous population of low mass subhalos, and by this I mean masses below approximately 10 to the 8 solar masses, may be statistically detected by their collective perturbation and images. And Yasser Hesave and collaborators pointed this out a few years ago in a very nice paper. So the key question that we asked with my group is, if we actually go and measure this power spectrum of substructure, what can we learn about low mass subhalos and relatedly about the nature of dark matter? This would be actually very promising since it can measure directly the dark side of galaxies. So in a paper with Ana Diaz-Rivero, my PhD student at Harvard, who actually just recently graduated, and Francis Yancy Racine, a former postdoc who is now a professor at the University of New Mexico, we developed a general formalism to study the endpoint correlation function in principle of the convergence field. And we started from the easiest, the power spectrum. So if we have a lot of structure, the perturbations will look very close to Gaussian, right? The central limit theorem will kick in, and most of the information should be in the power spectrum. So what we did is we modeled the convergence field. And when I say the convergence field, I mean nothing more and nothing less than the adimensional surface mass density. So we model it as a substructure component, which is what we care about, superimposed on a smoothly varying background density profile of the host. So here the convergence field of the substructure depends on the substructure position, mass, and intrinsic properties of the subhalos that might determine the density profile, for example, the truncation radius. And so what we did in this work is we proposed a change of language, moving away from talking about subhalos, and instead we proposed to talk about the correlation function of the projected density field. And so in this sense, we don't need to define what a subhalo is and what is not, as it is generally done in the literature. So we started from first principles. This has been done actually for the large scale structure a long time ago. And since when I first started this work, I was more familiar with this area. I borrowed their terminology. So here we are essentially applying the same kind of philosophy, but for smaller scales. Okay, so we describe the power spectrum in terms of a one subhalo term, which arises from ensemble averaging over the spatial distribution of a single subhalo, and a two subhalo term, which arises from averaging over pairs of distinct subhalos. And here we are taking integrals over different probabilities of the mass, of the intrinsic properties, of the spatial distribution within the host. So this is our result. Here is our power spectrum. And we can see that the power spectrum is mainly described by three quantities. We can see at low K, we have a plateau, a constant amplitude. And here we are probing scales much larger than any subhalo. So at these very large scales, all the subhalos are essentially point masses, and the Fourier transform of point masses is just white noise. And this is what we see, okay? The amplitude depends on the average abundance of substructure as well as different mass moments. As we move to small scales, we can see over here a turnover. This turnover corresponds to the truncation radius given by tidal interactions of the largest subhalos in the lens galaxy. And if we keep moving to smaller scales, we reach what we call an asymptotic regime, where the power spectrum asymptotes to a constant power law, which for example, for an NFW profile that describes well the CDM scenario, it goes as k to the -4. Now, if we have a non-trivial dark matter scenario, and by this I mean any dark matter scenario that is not CDM, the density profile will change. A scenario that, for example, has been well studied in the literature, proposed to solve some of the discrepancies seen between observations and simulations and continue to be studied, is the so-called SIDM scenario, strongly interacting dark matter. It has been shown that this scenario gives rise to a chord profile, as we can see in this figure over here. This is the chord profile in comparison to the truncated NFW profile. Now we see that at small scales, we change the slope, which reflects the fact that SIDM subhalos inner density profile looks different. It goes as 1/k to the 8 instead of 1/k to the 4, as I told you, it went for CDM. And note here that we can see a difference, we can see a very large difference, but the largest difference corresponds to very small scales, 1 to 100 parsec, which are scales that are difficult to reach in the near future. So we have in principle, we have a very big difference, but it is very hard to observe. However, we realized later on by looking at simulations that we could use information at larger and more accessible scales by adding redshift information. So this is what we did, and this is what I will show you here. Once we had our formalism built, and before looking into the data, we decided to test it in simulations. And for this, we used Mark Vogelsberger's simulation. Mark is a professor down the road, not that it matters these days, but he's a professor down the road at MIT. And he gave us his simulations for a CDM case and for an exotic dark matter scenario. In this particular case, it's a case with SIDM plus a cutoff in the initial power spectrum. And so here you can see a snapshot of these simulations for CDM and for the exotic dark matter scenario. And so it's already clear by eye the lack of small scale power for the exotic dark matter scenario. You can see already by eye the more abundant small scale power for the CDM scenario in comparison to the exotic dark matter scenario. So what did we see? Well, first we saw that our predictions matched the observations very well. Let's start with the CDM case, which is this panel on the left. So the different lines show different redshifts. As we evolve in time, we go up in these different lines, okay? So as we approach redshift equals 0, we expect more subhalos are accreted into the host halo, implying that the amplitude of the power spectrum increases, which is what we see, okay? For the exotic dark matter scenario, SIDM plus a cutoff, mass loss due to tidal interactions becomes important. And this leads on average to a reduction of the effective subhalo mass between about redshift of 0.5 to 0, leading to a net transfer of power from larger to smaller scales in the power spectrum. Furthermore, the much larger total number of subhalos in the CDM case also means that the two subhalo term makes a non-negligible contribution at z equals 0, which tends to increase the magnitude of the redshift evolution in this case. In contrast, the exotic dark matter scenario model does not get a significant two subhalo contribution at redshift equals 0. Another important aspect of this redshift evolution is the difference in the power slope for scales now of wave numbers greater than 2 inverse kiloparsecs, which are scales that are within reach in the near future by the Hubble Space Telescope, HST, or ALMA. This SIDM plus cutoff simulation has a lower central density of subhalos, making it more susceptible to tidal effects and mass loss. And we indeed find that substructure mass fraction in subhalos with masses less than 10 to the 7 solar masses grows more rapidly between redshift of 0.5 and 0 compared to CDM. So this can be this can potentially be a very powerful probe of low mass dark matter clumps. So this is actually observable. I borrowed this slide from Ana Diaz-Rivero because I think it is a neat diagram that describes the bridge that we are doing between theory and observations. The reason why we like the convergence power spectrum so much is that it gives us a way of mapping what we have, a strong lens image, to what we want, a dark matter theory. And the way that this is done is by the fact that the convergence power spectrum can relate a length scale that comes, for example, from deflection, well, comes in this case from deflection vectors of the lens plane to a mass scale, which gives, which is given by the halo and subhalo mass functions. And this is what the dark matter theories give you. So the convergence power spectrum can be seen as a nice bridge between the two sides of this diagram. We saw that the convergence power spectrum of subhalos within lensing galaxies is a promising observable to study dark matter. However, the distances involved in strong lensing systems are vast, and we expect the relevant volume to contain line-of-sight halos that are not associated necessarily with the main lens. Recently, in a paper led by my two graduate students, Can Sengul, who is actually from Turkey, and Arthur Tsang, we developed a formalism to calculate the effect of line-of-sight halos. I will call them perturbers or interlopers indistinctively in this talk. We developed a formalism to calculate this effect, the effect of these halos, as an effective convergence power spectrum. Now, instead of having a single lens plane at some redshift, we have any number of lens planes, as you can see in this figure over here. And instead of using the vanilla lens equation, we now have a recursive lens equation, which couples the angular deflections of successive lens planes. So by assuming that the perturbations due to the line-of-sight halos are small, we show that they can be projected onto the main lens plane as effective subhalos. So we define an effective convergence, modifying the internal properties of the halos, and we could then write an expression for the interloper or perturber power spectrum. The features of this power spectrum are very similar to the ones I showed you just before. So we have a convergence profile over here. We have a convergence profile which with a rescale radius, a mass distribution here with which now also depends on the comoving distance, and a probability distribution of the intrinsic properties over here, which is also now a function of distance. And finally, we have now a completely new ingredient, which is a selection function, okay, that tells you how to weight interlopers depending on whether they are foreground or background. We tested our formalism by simulating lensing systems using the full multi-plane lens equation, and found excellent agreement with our analytical prediction. So what I'm showing you here is a test of this formalism for a particular set of parameters, okay, as an example. So here we have a fiducial system with fraction of dark matter, halo mass in substructure of 0.4%, just for completeness, I'm giving you this number, between 10 to the 5 and 10 to the 8 solar masses. And here we can see that the line of sight halo contribution to the power spectrum is at least 7 times greater than the subhalos for source redshifts that we consider here. Source redshift of 1 and lens redshift of 0.5. In the reddish colors, so here in the reddish colors, we are seeing the interlopers plus subhalos, and in green we are seeing the subhalos. But of course, we cannot make from here a global statement. This depends on how many interlopers versus how many subhalos there are. And so what we did is we showed how the relative contribution of line of sight halos and subhalos depends on the source and lens redshift, as well as the assumed halo and subhalo mass functions. So to understand this, we fix the halo mass function and we vary the amplitude of the sub-halo mass function, okay? So what I'm showing you in these different panels are different amplitudes of this sub-halo mass function. Redder colors show the interlopers dominate and bluer colors show that subhalos dominate. And so pretty intuitively, we see that as we increase the amount of substructure, the colors go from red to blue, right? The question is, which of these three panels we are observing in practice? And we don't know exactly what this F sub, the fraction of substructure, is. But people place upper limits based on measurements of different systems using gravitational imaging. And what we can see is that having a substructure, what we saw looking at the literature is that having a substructure fraction of 2% is very unlikely for the mass scales that we are considering. It is much more likely that we are in a scenario like the ones that over here, okay, below 1%, meaning that the interlopers are dominating. And this is good news in that a measurement of the power spectrum may be measuring the halo mass function instead of the sub-halo mass function. To be more specific, we overlaid points that correspond to the Bells and Slacks families of galaxy-galaxy lensing. These are two well-known high-quality sets of lensing images. You can see Bells and Slacks families over here. And in particular, these are sets that have been used to place constraints on dark matter. So we can see that for both sets, for a fraction of substructure that we think is more realistic, they are dominated by the halo mass function. So for current images used right now to put constraints on dark matter, it is much more likely that people are actually probing the halo mass function as opposed to the sub-halo mass function. And the fact that under many lensing configurations and reasonable sub-halo population assumptions, the interloper contribution dominates the signal can be good news for the capacity of strong gravitational lensing to constrain the particle nature of dark matter. The amplitude of the convergence power spectrum can essentially be tied back to a mass function. So in order to translate a power spectrum amplitude to a dark matter theory, it is very important to understand whether the subhalos or interlopers are the dominant contribution to the power spectrum. Otherwise, we can obtain bias constraints on dark matter, and we could falsify the CDM scenario wrongly. The subhalo mass function is very hard to pin down. It depends on the host mass, and it evolves with redshift. So how it is affected by subhalos traveling within the host dark matter halo, as well as due to any variance in the host, remains an open problem. And in comparison, halos that are only subject to large-scale tidal fields have relatively calmer lives, and their evolution is better understood. So therefore, having a window into the smallest dark matter scales in the universe without relying on subhalos, but instead on halos, can make gravitational lensing a much more powerful and reliable probe of dark matter. So now I would like to talk about the road ahead. In terms of the road ahead, the Vera Rubin Observatory, formerly known as LSST, will discover tens of thousands of lens galaxies. And this vast increase in sample size will provide much stronger statistical constraints on dark matter. With a group of cosmologists working on dark matter, we submitted a paper last year that points out the advances that we will be able to make in the dark matter frontier once the Vera Rubin Observatory has its first light. And we also pointed out how we could actually extract dark matter information from measurements done by this observatory. And now the Vera Rubin Observatory team, which has been historically a dark energy survey, has added dark matter science to their formal agenda. So now let me talk briefly about how direct detection is done to resolve individual massive perturbers, to then tell you about our fast techniques of doing this. So the quintessential method for direct detection is called gravitational imaging. The idea is the same as what was proposed 20 years ago by Mao and Schneider. If you have some dark clamp lying close to an imaging projection, there might be some visible distortion that you can try to reconstruct, okay? That's the idea. We start with the data, a strongly lensed image, and the prerequisite is to model the smooth component of the lens, assume that the object doing the lensing has no clamps, and you model model it by a smooth component. So this is a model of the lens. We also, another prerequisite is to reconstruct the source. And once you have these two components, you can come up with a smooth model image that I'm showing you here. So once you have these two components and a smooth model image, you can then take the difference between the actual image and get your residuals. And the idea is to minimize these residuals by placing small potential corrections. Then you can get the potential corrections and relate them to the reconstructed surface mass density. And these overdensities, if significant, of course, will be pointing to new dark matter subhalos. For example, in this Nature paper by Veghetti and collaborators, they claimed a 12 sigma detection of a subhalo that you can see here, in particular, this subhalo, I believe, was 10 to the 8 solar masses. Now, direct detection of substructure is computationally very expensive, taking weeks to analyze each system, and most of the time, one gets null detection. Lens modeling is not straightforward, and the additional processing makes the process slow. To put this into context of how hard this problem is, so far, only 2 detections were claimed using this method in tens of images analyzed over months and months. Up to now, this pool of lens images has been small, so it can be done this way. But in the next few years, we expect this number of images to increase by many orders of magnitude. So what motivated us, together with Ana Diaz-Rivero, was the following question. Can we automate a procedure like direct detection using convolutional neural networks, making this process much faster, avoiding the step of macro modeling? So in this way, the promising candidates can go into this much more detailed analysis pipeline, whereas the vast majority that don't have substructure don't have to see all this time and resources spent on them just to get a null detection. And if you understand the sensitivity of your machine learning model well enough, you can still combine detections and non-detections to put constraints on dark matter, on different dark matter scenarios. So the costly step of our procedure was to simulate high fidelity, high quality, strong lens images. To do so, we used a publicly available code called Lenstronomy, developed by Simon Beerer, who is now at Stanford. This is an example of the individual components that go into simulating the final image, okay? We vary the macro model and the source together with the subhalo population in every image. There are many degeneracies between these parameters, so it was not trivial at all that a network could learn. For the source, we modeled it as a superposition of different clamps. We vary the ellipticity and the position of the host relative to the source. And for the images with substructure, we modeled them as NFW profiles, and we took the subhalo mass function to be a power law. We convolved the image with a Gaussian PSF, point spread function, with a width of 0.07 arc seconds, and we added Poisson noise. And we use this width because we wanted to be following close enough the images that we get from the Hubble Space Telescope. We also tested for correlated noise, and for this we used the Gaussian process, okay? And HST images might have correlations due to drizzling, for example. And so here, these different L's correspond to different correlation lengths. So we turned the problem into a binary classification task. We asked the question, for what mass ranges of substructure is the network able to recognize the lens as having substructure versus not having any. And the expectation, of course, is that for very low masses, the network will not be able to detect anything. But if the masses are high enough, if we have massive enough systems, the network will be able to detect it, analogous to what happens with direct detection methods. This is what we saw. We first simulated a subhalo population with one subhalo, okay? On the left panel, I'm showing you noise that is uncorrelated, and in the right, we vary the correlation scale, as you can see in the different colors here. Now, what we see is that for low values of the subhalo mass, okay, so here I'm showing you the macro model and then the different subhalo masses, and here I'm showing you the accuracy of our machine learning model. So what we see is that for low values of the subhalo mass, the accuracy lies well below 50%. And this may sound surprising because you're thinking, well, if I have a binary classification problem, so I should at least get 50% if there is like, you know, zero certainty. But this reflects the fact that to the network, these images are indistinguishable from macro-only images. Then for 5 times 10 to the 9 solar masses and above, the accuracy got better than 75%. And of course, it gets better when the noise is reduced. And unsurprisingly, the accuracy takes a hit when you add correlated noise because it can mimic the signature of a perturbation caused by a small subhalo. Then we went ahead and we tried both fixing the number of subhalos and fixing the fraction of mass in substructure, this F sub that I was talking about before. These 2 cases gave very similar results. Both are telling us that our network is sensitive to a massive perturber, analogously to direct detection methods. And we again find that subhalos have to be above 5 times 10 to the 9 solar masses for this particular architecture, okay, in order to have a 75% accuracy or better. This is comparable actually to the numbers cited in the literature for real detections, for real direct detections. Masses cited actually tend to be lower because they do not take into account projection effects when going from 3D to 2D. So in this work, we showed that small scale substructure can be inferred directly from astrophysical images by using convolutional neural networks without any intermediate modeling of the lens galaxy. And it actually takes much less than a second to analyze a system versus several weeks of traditional analysis. Okay, so we actually pointed out in this paper that this was a first proof of principle, but we could actually potentially do much better changing the architecture used. And so what we did then is to move on to use UNets. And this is a network well known for its success on image segmentation. I did this work again with Ana Diaz-Rivero and with my postdoc, Brian Osdiek, who was carrying out the work. Image segmentation is the problem of taking an image and trying to understand what are the individual components that make up this image. So here what we did is we teach the network to reconstruct the convergence field by classifying every single pixel in the image as belonging to the background, the main lens, or one of 9 different subhalo mass classes, okay? We just divided the problem into 9 different subhalo mass classes. And the network takes as an input a strong lens image. And this is basically what we want the network to predict. So here is the target, okay? So this is the image. This is a target that I'm showing you here as an example of a main image and a very low mass subhalo. And this is our prediction. So most of the pixels, as you can see, are in the background in black. There is the main lens, this light blue color. And in this case, there is a very small subhalo with a mass of 10 to the 6 solar masses. So what the network outputs is this 11 panel. Okay, these 11 panels over here are the outputs of the network. And for each class, we can see what is the probability of each class. So bluer colors correspond to higher probabilities and redder colors correspond to approximately 0 probability. So you can see that the network is very confident here on what it identifies as background and the main lens. Okay, we can see that for background, this is blue. For the main lens, it's very confident. That is the main lens as well. And surprisingly, it is also very certain that this over here corresponds to a very small subhalo. You can see that there is a little bit of artifacts that creates a fake pixel with mass over here. You can see these fake artifacts over here, but they are lower probability. So this really surprised us. As a disclaimer, there is no noise in this example. So then we moved on to add noise, and we can look at, and here I'm showing you this problem a bit more statistically by studying the confusion matrix, okay? So each column here is normalized to 1 and it gives the pixel probability. And so here we are seeing the prediction versus the target, okay? And the fact that it's diagonal tells you that the accuracy is very good. Most of the pixels are predicted to be in their true class. That's why it's diagonal. You see some of diagonal elements, but most of them correspond to the adjacent mass bins, okay? That makes sense because the masses of subhalos are continuous, whereas we are artificially choosing discrete mass bins. So of course there are edge effects. Also for the very low masses, you can see that there are quite a few pixels that get confused with the background or the main lens. And this makes sense again, because we are looking at these very teeny tiny perturbations. So when we add noise, which is noise that we chose, by the way, to be HST-like noise, it's realistic, we see that now the network, of course, struggles to find the low mass subhalos. And this is because the level of noise is above the pixel brightness changes due to the presence of these subhalos. And we can exactly map the pixel brightness changes to the noise and understand perfectly well why our confusion matrix shows us that we stop working for that particular mass, that we stop working given the noise. The network can find many subhalos. So we trained it to find one subhalo. It can find many subhalos. It can also find, we trained it with one lens. It can also find different lenses. So we were very excited about this prospect. So what we did is we combined many images to place constraints on the subhalo mass function instead of having to do some additional post-processing. So we find that if we combine order of tens images, as I'm showing you here, we can get errors on the slope of the subhalo mass function of about 10%. But of course, as we increase the number of images, the error bars decrease, as you can imagine. And if we combine 1,000 images, we get errors of 1%. And this is true for images with and without noise. So this is very, very exciting. Okay, so I arrived here to my concluding thoughts. So in summary, I showed you how we can learn important clues about dark matter physics by studying cosmological and astrophysical small scales. I showed you how the convergence power spectrum relates length observables to math scales that are given by dark matter theory. So here we have a nice bridge between length and mass scales. I showed you how we can use gravitational lensing to probe an untested regime of the CDM scenario. And this untested regime corresponds to kiloparsec scales. We also saw that the dominance of line of sight halos or interlopers in strong lens systems opens up actually a promising avenue in the search for dark matter. We can actually map more cleanly our observations to dark matter theories. And finally, I talked about machine learning methods that we have been developing with my group over the past years, 2 years. And we saw that machine learning can accelerate direct detection efforts by circumventing the lens modeling step, and it can accelerate it by a lot. We can go from spending weeks or months in traditional analysis to actually doing this in less than a second. Finally, more generally, I want to say that this coming decade will bring a wealth of new and complementary cosmological data. And it is very important that we use these different data sets and we also combine them and use its complementarity to have a better understanding of our universe. So hopefully, if we continue to exploit these measurements in new ways and continue to look off the beaten track, we will shed light on the dark sector soon. Thank you.
Thank you for this very nice, comprehensive, exciting, and energetic talk. Now we can pass. Now we can pass to questions. Please ask questions, sending a message through chat button.
So I'm seeing here, shall I read the questions? Shall I take the questions?
Yeah, sure, please.
Thanks for the talk. Would you expect to find satellite galaxies tracing the same substructure you find with lensing? Would satellites be a complementary probe, or are they too large and sparse? Well, so of course you can detect satellite galaxies with lensing, depending on, many satellite galaxies have been, when we talk about satellite galaxies of the Milky Way, like the well-known Draco or Nax, we're talking about this type of masses, perhaps a little bit more massive, 10 to the 8, 10 to the 9 solar masses. So yes, you can expect to find any mass using gravitational lensing. We would not call this substructure, we would call it just, the galaxy itself. But yes, gravitational lensing, the nice feature of gravitational lensing is that it really doesn't depend on the interaction of dark matter with anything. It's just, it's the most direct probe that we have of dark matter because it directly probes the gravitational effects.